This is the instrument binnacle from a 1958 Oldsmobile, which is clearly an American car. And the reason I've got it is because the wiring at the back of the panel needs a fair bit of attention. I'm going to turn it around so that you can have a look at the back in a minute, and you'll see there's a printed circuit board which has certainly seen better days. So I'm just going to turn it around now. And here we can see the circuit board. So you can see there used to be a connector here, and this connector has clearly been damaged in some way, and the wiring has been fitted directly onto the circuit board. There are several missed tracks, and also the copper coating on the circuit board has been quite badly damaged. Now these holes are for light fittings, and those light fittings, which just clip into the holes, illuminate the various gauges and indicators on the panel itself. So we've got a generator indicator, we've got an oil pressure indicator, we've got a over temperature indicator from the engine, we've got a cold indicator which I think is from the air temperature inside the car. We've got right and left indicators, we've also got a main beam indicator, and then we've got illumination for the speedo itself. What I'm going to do is just pop the circuit board off, and then we can have a slightly closer look at it. These two connectors, by the way, are for the fuel gauge. So here you can see the condition of the circuit board. It really is in very poor condition, but considering it's 60 years old, it's probably not done too badly at all. And it was more than likely from a very early example of printed circuit board technology. So the intention is to replace this circuit board with a brand new one, and that will mean reverse engineering this circuit board so that we get the correct outer profile and the correct positioning for each of these holes. And we also need to position these clearance holes, which are for these screws here. Not a particularly taxing job, but nonetheless quite an interesting one to see how we go along with it. So the next video I'll show you how I set about doing some CAD modelling and how I set about generating the printed circuit board information that we can manufacture a brand new one from. So the first step in reverse engineering this circuit board was to do measurement of all of the various features, and then transcribe those measurements into a CAD model, and we can see the result of that CAD model here. So we can see the general outline of the board, which we've created by measuring the various features. We've created a outline for the cutout for the light fittings, and we've included those into the model. We've also included all of the holes through the circuit board, which act as either connectivity pads or as clearance holes for the various features on the circuit board. I was then able to print this out on a one-to-one drawing and just compare that with the original board and just check that all of the features are in the correct place. Once we know all the features are in the correct place, we can then create some CAD data that I can transcribe into the printed circuit board layout, and I'll show you that next. Okay, so once we've created the CAD model, we can export the outline of the board to a suitable file that can be read into the printed circuit layout program. And you can see here the green line has been imported from the CAD data, and we can see that we've got cutouts for the light fittings, cutouts for the clearance holes for features that are on the instrument panel itself. And that is the outline that the board cutter is going to go around in order to cut this board out. What we can also see on here is a layer that's called the silk screen, and that will be printed onto the circuit board as viewable, readable information, and we can change that, maneuver it, put it wherever we wish. Now, when the board is made, there are two electrical layers or copper layers on the board, one on each side, and these are called the top copper and the bottom copper layers. They start out as a continuous plane of copper, and the parts that we want to keep are masked off with a special mask, and the remaining copper is then etched away. So what we want to do is to tell the board manufacturer what bits of copper we want to keep on both the top layer and the bottom layer. So I'll turn those layers on and you can see what they look like. Okay, so we can see in red we have the layer that's going to be on top of the board, and that includes these grey areas, which are going to be pads for holes that go through the circuit board. We can see another set of holes that are through the circuit board for a connector that's going to connect onto the vehicle electrics. These two pads are for the fuel gauge, which are part of the instrument panel, and these pads are for screws that connect the ground line down to the vehicle 0 volts. We can also see that there are areas here that are for the light fitting to be able to pick up on the electrical layers. The blue line is on the reverse side of the board, so that is the bottom layer. We also find that these pads appear on the bottom layer as well, and that part of the manufacture process is to deposit copper between the top layer and the bottom layer on the inside of the hole, called plated through holes. Now, in addition to this, there is a further layer that's deposited onto this board, which is effectively a paint layer or an epoxy layer, and it's called the solder mask. And the solder mask will mask off all of the copper that we want to ensure cannot be soldered onto or will not be exposed for some reason, as part of the operation of the circuit board. So the solder resist layers, I'll just pop those layers on as well. So we can see here now the grey areas are the bits of copper that are going to be exposed, and all the remaining areas are going to be hidden by this copper, by the solder resist layer. Once we've generated this, what we then do is to output a set of files, one for each of the layers. So we've got the board outline, we have the top silk, we have the two resist layers and the two copper layers. These all appear as separate files that are then sent to a circuit board manufacturer who then interprets all of those files, puts them all together and creates a circuit board out of them. And what we'll see in the next video is what the circuit board looks like once it's been returned back, and we will be able to fit it onto the instrument panel, see how well it works. Right, well, we've got the circuit board back and this is what it looks like, and I'm sure you'll agree that it's a much better example than the original one that was taken off. What you'll see is that we've fitted a different connector here, which allows the instrument panel to be easily disconnected from the vehicle's wiring. We also have these bulb inserts. Now I've replaced these with a slightly different size of insert, and they also have LED bulbs in them rather than the original incandescent ones. So once that popped back in place, what we can see is that the board neatly fits in place of the original ones. The holes are ever so slightly misplaced, but they're certainly not bad enough that that it won't fit. And by just putting the screws back in, we can see that it fits quite nicely. Okay, now I've also made a wiring connector. So this is the mating connector that will go off to the vehicle's wiring, and you can also see here I've got a strip, terminal strip here, so that we can attach the vehicle wiring into this terminal strip. And once we're satisfied that the vehicle wiring is all connected correctly, we can then very quickly and easily just disconnect it from this single connector. So by popping that into there, we're all connected up and we're all ready to go. So the next video will show how I test the panel to verify that all of the lights are working correctly.